Hello and welcome to the last of the lectures in this week 9 of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will look at continuous models that can be obtained from similarity-based reasoning. A quick recap of the mechanism of the similarity-based reasoning inference schemes. We are given a set of CISO if-then rules. Given an input A dash, first thing we do is match the input with each of the antecedents AI. We use a matching function for that and obtain n similarity values Si. In step 2, these are some examples of matching functions we have seen earlier too. In step 2, we take these similarity values Si and modify the corresponding consequent of the rule, ith rule. For this we use a modification function. So the modification function j is essentially from 0, 1 cross f of y to f of I. However, we have seen that it can be seen as a binary function on the unit interval. These are some examples of modification functions that by now we are quite accustomed with. In the third step, all of the modified consequent fuzzy sets, bi dashes, they are all aggregated using a function g. For this, we use a function g which takes two or more fuzzy sets on y and gives us out a fuzzy set on y. We have seen that this g can be considered once again as a binary function on 0, 1 along with the associativity property. Now, if we stay within the realms of mapping from fuzzy sets to fuzzy sets, this is sufficient. However, often there is a need to defuzzify the output fuzzy set, or the input may be in the form of a real number or real vector which needs to be fuzzified. So we need a defuzzifier and a fuzzifier as pre and post processing steps. Now, this is the general form of a fuzzy inference mechanism. In the case of an SBR, we know these are the corresponding components. Px and Py are the fuzzy coverings on x and y respectively. R of AABJ gives us the fuzzy if-then rule base, where these AIs and BJs, the antecedents and consequents, are actually picked from the fuzzy coverings Px and Py. M is any matching function, J is any modification function, G is any aggregation function, H is the fuzzifier, and small g is the defuzzifier. However, if you look at SBR as fuzzy mapping, that is a mapping between the set of all fuzzy sets on X to set of all fuzzy sets on Y, then the fuzzifier H and the defuzzifier small g, they do not play a role. So these are the factors that will affect the inference. And given this, how will the overall function look like? We denote it by psi tilde. So given A dash, the corresponding b dash of b dash, which is a fuzzy set on y, is specified like this. B dash of y is, we are aggregating over the rules. Given an a dash, first we find the similarity value with each of the antecedents using the matching function. Use this Si to modify the consequence, the corresponding consequence with the modification function j, and then aggregate it using the function g. Well, let us revisit the continuous model of an FRI and define the continuous model of an SBR accordingly. So we have this system of if-then rules. Now we are looking at a fuzzy inference system as a mapping between fuzzy sets and the antecedent consequent pairs as coming from the corresponding Cartesian product of the input and output fuzzy spaces. Based on this, we said a psi tilde is a continuous model for the given rule base if and only if this particular inequality is valid. Of course, we decoded or interpreted this as the continuity equation or inequality because we could show that in some sense it is giving us Lipschitz continuity at the points ai, bi with respect to a particular metric that we have actually constructed from the additive generators of T-nodes. Now, we will try to do a similar thing now. Once again, we have the rule base. Let us assume there are metrics defined on the input and output spaces. They are given as dx and dy. And now we are looking at the system function of an SBR psi tilde as a mapping from f of x to f of y. We define psi tilde to be a continuous model for this given rule base if for any input a dash coming from f of x, and for every epsilon, any epsilon greater than 0, if we are able to find a delta, of course this delta will depend on both a dash and epsilon, such that whenever a dash is delta close to ai on the input space, then we want that the output from psi tilde at a dash is epsilon close to bi with respect to the metric that is defined on the output space of fuzzy sets y, f of y, and this should happen for every i. So this is what we would like to define as the continuous model of an SBR, and this is how it has been dealt with in general in FRA also. We want to base it on the given ground truth of values, which are these pairs of fuzzy sets. This is what we call fuzzy points, ai, bi, which are the antecedents and consequence in the fuzzy if-then rule base that is given to us. With this definition, let's try to proceed further. That means we need metrics on the spaces of fuzzy sets. Let us look at a few examples of such metrics. We have seen one in the previous lecture. We will see a few more in this lecture. By fbn of x, given an x, we denote the set of all bounded normal fuzzy sets on x. fbnc would mean bounded normal and continuous fuzzy sets on x. bns would imply bounded normal and symmetric fuzzy sets. And by this f infinity of x, we consider normal and convex fuzzy sets, the set of all normal and convex fuzzy sets defined on x, but they need not necessarily be bounded. So now we have seen this particular metric in the previous lecture that was proposed or defined by Pafiliev and Lemke in their earlier work, 2006 work. We know that this is a metric on the space of all fuzzy sets, and in fact specifically on the space of all bounded normal, symmetric or continuous fuzzy sets, it has some interesting properties too. Of course, note that this f is the additive generator of a continuous T-norm, not necessarily strict. It could also be generalized to the case of non-strict or nilpotent T-norms. But yesterday, for convenience sake, we have seen it coming from the strict T-norm generators. Of course, in that context, the purpose was to interpret the inequality, which we called as the continuous model inequality, because that is what was specified as to be satisfied for a psi tilde to be called a continuous model of the given rule base. So in that limited context, we considered only the additive generators of strict T-norms. Now, on the space of unbounded fuzzy sets, we could define such a metric where this u alpha and v alpha, the alpha cuts of u and v, and dh is the Ostov metric, the usual Ostov metric on the set of compact subsets of x. If we consider bounded normal, symmetric or continuous fuzzy sets on x, we could also define such a metric where by this mod operation it could denote either the cardinality in case it is finite, or the length if it's an interval, or the measure of the set. Now we will need to deal with continuity of binary functions. So let's look at how to define continuity with respect to product metrics. So if you have two metric spaces x and y with the corresponding metrics dx and dy, an f from x cross y to r is said to be continuous at a point x dash y dash if for any epsilon greater than 0 there exists a delta, once again depends on the points and also the epsilon, such that dx of xx dash plus dy of y dash less than delta implies with respect to the corresponding metric defined on R, the function values at xy and x dash y dash, the distance between them, dr of fxy f of x dash y dash should be less than epsilon. Of course, this is one way to define continuity. Instead of taking the addition, the sum of these two values. We could also take the max of these two values and insist that when this is less than delta, then we want this to happen with respect to the usual metric on R. Well, to discuss continuous models of SBR, we know that there are many factors that go into making the SBR inference mechanism: the modification function, the matching function, also the aggregation function. So these components also need to be continuous in a certain way. Let us look at those specifications. Now, in the case of SBR, as a mapping from f of x to f of y, these are the components, and px and py are the coverings, ai's are the pieces in the partition, similarly bj are the pieces in the fuzzy covering over y. Given fx and dx is the metric on it, and the unit interval 0, 1 and a metric d01 on it, we say M is continuous with respect to this covering px if for any epsilon greater than 0 and any ai that you pick from px, and given any two fuzzy sets a dash and a double dash coming from f of x, there should exist a delta depending on all these parameters such that dx of a dash a double dash, whenever it is less than delta, it should imply that d of 0, 1 of with respect to the metric defined on 0, 1, the similarity values of a dash to ai and a double dash to ai should be smaller than epsilon. Now remember, this ai is also picked arbitrarily, so we do not specify I separately again. So we pick an epsilon, ai and two fuzzy sets a dash, a double dash. For that we should have a delta such that whenever a dash and a double dash are delta close, then we know that similarity values to the a that we have picked is also epsilon close. So this is when we say the matching function is continuous with respect to the fuzzy covering that we have considered. Are there examples of such matching functions? Well, yes. Look at a covering of a set based on fuzzy sets which are bounded, normal and symmetric. Let's assume that these form a Ruspini partition of X. We could also assume X itself to be bounded. And let Xi be the points of normality of these fuzzy sets Ai. And given an A dash, which is once again coming from this FBNOS of X, so that means it's bounded, normal and symmetric. Let it attain normality at X dash. And consider these two matching functions. Now it can be shown, not without much difficulty, that if we consider these two metrics, the metric DAG on f of x and the usual metric mod on 0, 1, then both these matching functions are in fact continuous with respect to the px that we have considered and the metrics that we have listed out here. So there are examples of matching functions which are continuous with respect to a given covering of x. Now let's look at the modification function. We know that it takes a similarity value which comes from 0, 1, takes the consequent bi, which is a fuzzy set on y, modifies this and gives us a bi dash, which is again a fuzzy set on y. So it's a function from 0, 1 cross f of y to f of y. We say this j is continuous at a point s dash b dash. S dash is from 0, 1, b dash is a fuzzy set on y. If for any epsilon greater than 0, there is delta greater than 0, such that max of this quantity, whenever it is less than delta, then we want that the corresponding modified fuzzy sets with respect to the metric on y is less than epsilon. Now this is the usual definition of continuity with respect to the product metrics that we have considered. Note that we have seen that j typically can be considered to be a binary function on the unit interval. What needs to be seen is we can have a j which perhaps is not continuous on 0, 1 square, but still j may be continuous on this set. It means j may be continuous as a function on 0, 1 cross f of y to f of y. Now let's look at an example. Let's take the Gauguin implication, because for modification often we use the implication function. Clearly the Gauguin implication is not a continuous implication. Let's consider two fuzzy sets b and b dash. these are the fuzzy sets that we want to modify. Let's assume that S is the similarity value coming from 0, 1, with which we want to modify this B. This is the value S. Now using the Gaussian implication, if we modify this, then this is the modified fuzzy set that we get. Similarly, you can also note that at this point where S is, it attains normality because y by x, so it goes above 1. It touches 1. So similarly, if this is the similarity value S dash, using this, if you are modifying B dash, this is how it would look like using the Gaussian implication. Now, it can be clearly seen, can be proven based on the formula that whenever SS dash and BB dash are such that this inequality is held for any given epsilon, we can find a delta such that if this is smaller than delta, then using the same metric on y, the corresponding fuzzy sets BB dash are in fact less than epsilon. So it can be shown that continuity can be had even when the function j that we use is not a continuous function on 0, 1 square. However, we should be careful in choosing the j because the modified fuzzy set should again fall back within the space of fuzzy sets that we are considering for y. Consider, for instance, the Lukasiewicz implication and this particular B. Clearly, this is a bounded, normal, symmetric fuzzy set. So if you are assuming it to come from FBNS of y, look at what happens if you take the similarity value 0.4 and use the Lukasiewicz implication as the modification function. Then the modified fuzzy set is something like this. While it is normal and seems symmetric, it definitely is not bounded. So we should be careful in the choice of the modification function j, even if you are considering them to be binary functions on 0, 1. Well, we can again define the continuity of the aggregation function. So this takes a few fuzzy sets on y and gives out a fuzzy set on y. We say that for a fixed n, it is continuous at b1, b2, so on till bn if for any epsilon greater than 0, there exists delta greater than 0, such that when the maximum of bi, bi, bi dash, if this is less than delta, then this implies that the corresponding aggregated values should be smaller than epsilon with respect to the metric y that we have on f of y. Once again, we have seen that typically g can be any binary operation on 0, 1, but needs to be associated. And note that all the caveats that are applicable for j remain for g2. Now, with this, we are in a position to talk about continuity of the system function obtained from the similarity-based reasoning. Note that this is the form of the similarity-based reasoning that we are considering. And now given an a dash, the output b dash is obtained as follows. B dash of y is psi tilde a dash of y, which is nothing but this. Now, the main result on this topic of this lecture is this. Let Px form a fuzzy covering over x, that is, these are the ones that we pick from the antecedents. Py form a fuzzy covering over y. J as a function on 0, 1 cross f of y to f of y is continuous. G as a function on f of y cross f of y, so on n times n copies or some arbitrary copies of f of y to f of y is continuous. And M is continuous with respect to the fuzzy covering Px that we have considered. If you have all these things, then what we can claim is the system function of SBR, psi tilde, is in fact continuous as a function from f of x to f of y. Note that this result is stronger. It claims psi tilde to be continuous, not just a continuous model of the given rule base. So we'll take a look at the proof of this result. As was mentioned, it's a stronger result. We need to prove psi tilde is in fact continuous as a function from f of x to f of y. Well, what does it mean to show that psi tilde as a function from fx to fy is continuous? Given any AA dash element of f of x, we need to show, and any epsilon greater than 0, we need to show there exists delta greater than 0 such that whenever dx of AA dash is less than delta, this should imply dy of psi tilde of A dash comma psi tilde of A double dash is less than epsilon. So this is what we need to show. Let's look at what is the form of B dash itself. If you are given A dash, psi tilde of A dash is B dash. Now this is given as G over I is equal to 1 to N. So this is the formula that we have finally for psi tilde. J of M of AI comma A dash comma BI. So now writing this quantity as BI dash, we could write B dash as G of B1 dash, B2 dash, Bn dash. Similarly, psi tilde of A double dash is B double dash, can be written as B1 double dash, B2 double dash, so on to Bn double dash. Now let's make use of the conditions that are given to us. G we know is continuous. So now for the given epsilon greater than 0, there will always exist a delta 2 greater than 0 such that whenever match over I dy of BA dash, BA double dash, if this is less than delta 2, then this implies dy of G of B1 dash, Bn dash, comma G of B1 double dash, Bn double dash. Essentially, that is dy of B dash, B double dash is less than epsilon. So for a given epsilon, we know such a delta 2 exists. So let's mark this because of the continuity property of G. So now we also know J as a function of 0 1 cross f of y to f of y is in fact continuous. Let us fix an I from 1 to n and hence fix a BI. Now if you fix this BI from this space, then what we can see is, since it is continuous, for this delta 2 that we have, considering it as an epsilon locally, there will exist a delta 1 I greater than 0. This I is related to this I that we have fixed, such that mod m of ai comma a dash minus m of a I comma a double dash, this, whenever this is less than delta 1 I, this implies dy of b I dash b I double dash is in fact less than delta 2. Note that we are getting this because of continuity of of j. We have fixed, what have we done? We have fixed a particular I, and once we fix a particular I, we are fixing the vi, we are looking at what happens to j as a function of single variable, because one of the components we have fixed. We see that when delta 2 is fixed, looking at it as an epsilon, because of continuity of j, we see that for this delta 2 and a fixed I, there will always exist a delta 1 I such that mod m of ai comma a dash minus m of ai comma a double dash, whenever it is less than delta 1 I, this implies dy of bi dash bi double dash will be less than delta 2. Now note that this is for one I that we have done. So if we consider delta 1 to be minimum over all the i's, delta 1 I, then what we can say is m of ai comma a dash minus m of ai comma a double dash, whenever this is less than delta 1, this implies the corresponding bi dash bi double dash is less than delta 1. So our delta 1 is essentially the minimum of all these delta 1 I values. Well, we are almost there, the final step. Notice once again that m is continuous with respect to px, which is ai, I is equal to 1 to I. What it means is, if you once again fix an I, note that we fixed an I here, but we generalized it in the sense that we took delta 1 to be the minimum of all of them. So now this delta 1 will work across any I. So now in the next step we are fixing an I to again discuss as above. Let's fix an I. Now by the continuity of m, we know that for the delta 1 greater than 0, there exists, let's say, delta naught I greater than 0, such that whenever dx of a dash a double dash is less than delta naught I, this implies the corresponding matching values m ai a dash minus m ai a double dash, this will be less than delta 1. Note that this I is related to what we have taken. Now this is an arbitrary I because it is continuous with respect to every ai, the whole partition or the covering px. Now let's define delta to be once again the minimum over I, delta naught I, and clearly what we have is whenever dx, if a and a dash are such that they are less than delta, this implies mod of m ai a dash minus m ai comma a double dash is less than delta 1. Now this is the missing piece. Now we know that if this happens, then retracing our steps back, you can see that here itself, that whenever this happens, this will happen for every I. Now this would imply that the corresponding dy bi dash bi double dash, they are less than delta 2. Once again, this is for all I. Now retracing this step back, when this happens, we know that from here the max of them will also, for every I it is true. That means that implies dy of g of b1 dash bn dash comma g of b1 double dash bn dash is less than epsilon. But what is this? It's nothing but this quantity is b dash and this quantity is b double dash. So we know that this is less than epsilon. So this is exactly what we wanted to prove. We have taken a dash and a double dash to be arbitrary, and what we have shown is for any given epsilon, there will exist a delta such that if a dash and a double dash are close enough in the x space with respect to smaller than delta, closer than delta, then dy of psi tilde of a dash and psi tilde of a double dash, they are closer than epsilon with respect to the metric that we have on y. Now, interestingly, what we have shown is continuity of the psi tilde, the mapping obtained from SBR as a mapping from f of x to f of y. Now, what we are interested in is it also a continuous model for the given rule base? Now, let's look at some of the sufficiency and equivalence conditions that we have obtained for SBR inference scheme to have interpolativity. You might recall this from the last lecture of the previous week. If you look at it, towards discussing this, we had insisted on some properties on M specifically. Given a matching function M, we say it is consistent with the space from which the fuzzy sets are being taken, its domain essentially. We say it is consistent with its domain if for any A, M of A is 1, and we say it is consistent with respect to a fuzzy cover, much like how we said it is continuous with respect to a fuzzy cover. If we are given a fuzzy cover on X and an arbitrary A dash from f of X, we say that it is consistent with respect to this P if summation of the matching values of A dash to each of the pieces in the covering, their sum does not add up to more than 1. So sum is less than or equal to 1. Now, under this condition, we have seen that an SBR model is interpolative. What are the conditions? Px and Py are fuzzy coverings. J satisfies these two properties, that is NP and also what we call the falsity principle. G is commutative, associative and satisfies NP. And M satisfies both MCF, it's consistent with respect to its domain and also consistent with respect to the fuzzy covering Px. Then we have seen that the psi tilde obtained from here is in fact interpolative. That means psi tilde of AA is BA. We also had a couple of other results. One other sufficiency condition ensuring interpolativity is this, with Px and Py as fuzzy coverings on X and Y, J satisfying NP and J of 0y being 0. G is commutative, associative, and now 0 is the neutral element of Y, and M still satisfies MCF and MCP. We can then show the corresponding psi tilde is in fact interpolative. And finally, we have also seen some necessary and sufficiency conditions. Once again, Px and Py are fuzzy coverings. Now, the operation J is not an operation with NP and falsity principle. We specifically pick a residual implication. It means an implication, R implication from a left continuous T now, and G to be min. Then we say this psi tilde that we obtain from SBR is interpolative if and only if it satisfies this inequality. We have also shown that if M is commutative, then that inequality turns out to be this, where this is the biresidual. Well, why discuss these interpolativity results? The question is, when is psi tilde a continuous model of the given rule base? Now, putting all of them together, it is clear that this is the form of the SBR that we are considering. If Px, Py, M, J and G satisfy all the conditions of theorem 1 and all the conditions of any of theorems 2, 3 or 4 which are required for interpolativity, if they satisfy this, then it is clear that psi tilde is in fact a continuous model of the given rule base. This is immediate to see because what we have shown is for any A dash A double dash, dx of A double dash less than delta implies this. Now if psi is interpolative, psi tilde is interpolative, and if you give AI for any I, then we are going to get BI. So that means essentially what we will get here is dx of ai comma a dash less than delta implies dy of bi comma psi delta of a dash a dash is less than epsilon. This is essentially the condition that we need to satisfy for psi tilde to be a continuous model of the given rule base, of course, for every I that we have there. So putting all of them together, we see that we can talk about when an SBR is a continuous model of a given rule base. A few observations. Note that theorem 1 is in general stronger, and it is also general because we have not put any conditions on J except or G except on the continuity part. We are not asking for some boundary conditions on J. We are not insisting that they should come from a residual lattice or so. No? And it is also stronger in the sense that it is showing continuity between spaces. That psi tilde is actually a continuous function between spaces, not just continuous model of the given rule base. However, we are asking for a condition on M which ensures continuity with respect to the fuzzy cover Px. In this sense, we are also tying it up to the given rule base. Finally, if we allow the operations to come from residual lattice, as we have seen for interpolativity, we can get similar but very interesting results as in the case of an FRI, of course in the context of continuous models of an SBR. Well, the topics covered in this lecture are predominantly picked up from this work of Mandel and Jairam. With this, we'll wind up with discussing continuity or continuous models of fuzzy inference mechanisms of FRI and SBR. In the next week of lectures, we will begin by discussing robustness of fuzzy inference mechanisms. We'll clearly highlight how it is different from continuity and discuss their robustness. Glad you could join for this lecture. Hope to see you soon in the next lecture. Thank you again.